type of angular momentum today that the hydrogen atom has and experiences. And then what we'll do on Wednesday is do the radial problem, right? The finish up the hydrogen atom. Second half. We only need to spend about one lecture. That'll give us a really nice equation to solve for some wave functions. We'll get wave functions for the hydrogen atom. We'll look at the orbitals, get all the orbitals you know and love, the S, the P's, the D's. We'll look at all of that, and then next week what we'll do is we'll start looking at helium, start thinking about adding another electron to the system, and we're going to hit a roadblock in helium that we'll try to tackle a little bit, and then we'll kind of leave it at there. We'll start talking about general multi-electron atoms. We'll look at trends in atoms. We'll realize we're not going to be able to calculate wave functions for atoms bigger than hydrogen, at least in the sense that we can't write it down. Certainly compute them. We'll start looking at trends of atoms, things that we can learn about from hydrogen that teach us about what happens in other atoms as well. So we'll look at some periodic and atomic trends. And then we'll move on to molecules for the rest of the semester. Finish up with molecules. If you guys are in Comp Chem right now, you'll see some overlap between the final module of this course and Comp Chem right now. We'll probably do couple molecular orbital theory like you're doing in Comp Chem. And of course, I'll give it my twist. Okay, so let's continue about angular momentum. Let's just remind ourselves really quickly the gist of orbital angular momentum in the hydrogen atom. Remember, angular momentum is defined by two operators, the L squared operator and the Z component, LZ, right? And we apply them. Remember that our wave functions here for our system, for our angular system, which are functions of theta and phi, we have numbers L and M, quantum numbers L and M. And of course, these are the spherical harmonics, which have the label Y, right? These are our S orbitals, P orbitals, etc. We plot those if we ever need them. We'll just look up the functional forms. They're perfect. They're tabulated functions. They're known to everybody. These are what are called the spherical harmonics. Right? And they're just like every other wave function, they're normalized. They're normalized and orthogonal. Just like any wave function, satisfy all the properties of the wave function. And they're tabulated. You can find them on Wikipedia or in a book or something like that. They're tabulated. They're well known. Tabulated functions. Okay, so we don't really have to worry too much about those orbitals right now. We just know that they look like S's and they look like P's and D's and F's, right? We have a sense of what those orbitals look like. Gen Chem, just keep those in the back of your head. These are the states of angular momentum. They tell you something about where the electron is relative to the proton at fixed angular momentum. And then we have, again, the angular momentum is defined by two operators. One is L squared. And this is applied to psi with quantum numbers L and M. We get H bar squared L plus 1 back times our wave function. And L, of course, can take any value between 0 and infinity. Well, any integer. So again, this is what we call the orbital angular momentum operator. Right, it tells you something about the total angular momentum of the electron. And then we're left with the final one, which is the Z component of the angular momentum, which is H bar M times the wave function. Where M can take any value between minus L plus 1, dot, 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 L minus 1 to L. Okay. So there are 2L plus, what this basically means, if you think about it a little bit, this means there are 2L plus 1 CHEM states. When L is some number, you have 2L plus 1 different possible orbitals or different orientation stable orbits. Okay, so this specifies the total angular momentum of your electron's orbit, L squared. And LZ tells you about one of the 2L plus 1 stable orbits the electron can have with that fixed amount of energy. So there are 3 of them for L equals 1, p orbitals, 3 p orbitals, L equals 2. There's 5 stable orbits, which are the 5 d orbitals. For L equals 0, which is the s orbital, there's only 1. We looked at those fairly carefully last time, right? So this math is really easy, right? You really don't have to think that hard about it. Angular momentum has 2 states, right? The total angular momentum and then the projectional on the z-axis, right? That's one of the 3 directions. We can't do the other 2. And so the energies associated with rotation are just h bar squared, LL plus 1. And then each LZ state is split in angular momentum by m each bar. Now, how do I know that this is true? Right. Why? So one of the things that we mentioned previously in class was that maybe I should just revise this argument. We look at the classic Bohr model of the hydrogen atom. Right, Niels Bohr, before he knew anything about angular momentum or spin or anything like this, what he had was a hydrogen atom, and he has an absorption spectrum. The absorption spectrum of hydrogen had been known for about 100 years at this point, that hydrogen has these distinct absorptions. It doesn't absorb anything, it only absorbs specific energies. And it seems like there's a progression of lines. We'll look at this tomorrow. The spectrum of H, but you can you have an idea that if you've ever done, like if you're done any research with Dr. Marsico and you've done laser induced breakdown spectroscopy, atoms have these discrete lines that they absorb at. They don't absorb anything. They only absorb specific frequencies. And H is just like that. So Bohr had this model had this spectrum for H, and no one really understood why it only absorbs these frequencies. And what Bohr says, Bohr suggested that, hey, the way that the hydrogen atom may work is you've got this proton in the center, and the electron exists in stable orbits around the proton, right? So he labels these. There's different orbits of different sizes. He calls them n equals 1, n equals 2, n equals 3, and so on and so forth. Of course, what he's saying is that the electron is in one of these. So this is one of the electron states. Electron is orbiting, and these stable orbits satisfy the following energy conservation, which is that the kinetic energy from angular momentum is equal and opposite to the potential energy from electrostatic attraction. Right, so the idea is that the electron is spinning fast enough that the energy associated with that compensates the attractive potential of the protons of the electron, keeping it from sucking it up like that. And what Bohr says is that the frequencies, the wavelengths of the light, right? He says that the spectrum is consistent with absorptions between 2 different orbits. So he sees some absorptions delta E, which are going to be the energy, which are associated with the energy of, say, one state in prime minus the energy of another state N. Right, so he says that you'll see a line, you'll see the first H line at E2 minus E1, where these are the energies of these orbits. All right, so he calculates what the energies of these orbits are and stuff like that, and it lines up beautifully with the spectrum. So surprisingly, even though this turns out to be a wrong model for the hydrogen atom, Bohr gets, in some sense, the idea correct. He says that I should see absorptions if I can calculate the energies of these, the kinetic energies of these stable orbits. The energy difference between two adjacent orbits, E1 and E2, for instance, there should be an absorption line in the spectrum of that energy. And that's what he sees. He sees a line corresponding to these stable transitions between these stable orbits. And he says, okay, it works great, right? But the problem with Bohr's model is that the kinetic energy, right? These states are where the kinetic energy from angular momentum is equal and opposite to the potential energy from electrostatic attraction. Right? You always have potential energy. This is always non-zero. It's always attractive. And so that means that the angular momentum always has to be a non-zero amount. Right? The electron always has to have angular momentum. Right? So the consequence of Bohr's model is that L cannot be equal to zero for any state, right? Because you always have to have kinetic energy. And we've already shown that that's not true, right? Experimentally, and what we show for theory, proper theory from class, right? There exists a state where the average value of L squared to the 1/2 is equal to 0, which is kind of like the average value of L. I'm just going to write that. Right, so this is kind of like a, right? This is the s orbital, right? This is the y1 0 state or the 1s orbital, right? Which is a stable orbit. The electron is perfectly fine staying 1s orbital, but it has no angular momentum. But we need to be very, very careful with that statement, right? What it doesn't have is the value of L squared is 0. The average value of L squared is 0, right? Because if we're in the state, the 1s state, L squared, we're measuring L squared, we're measuring the magnitude of angular momentum, not angular momentum. 10, which is h bar squared. Oh, sorry, this is 0, 0. I apologize. 0, 0. L equals 0, m is equal to 0. 0 times 0 plus 1, which is 0. Okay, so it has no L squared. L squared is 0 for this system. That does not mean L is 0. Right? Remember when we talked about the harmonic oscillator, we asked the question, what's the average momentum of the oscillator? Or the average position, it measures 0. The average momentum of a harmonic oscillator is 0. That doesn't mean the oscillator is not moving. It just means that there's an equal probability of it moving in this direction as there's an equal probability of moving in this direction. So the momentum contribution from this direction cancels out this direction. And that's exactly the case here. In the 1s orbital, L squared is 0. That does not mean it has no angular momentum. It just means whatever angular momentum it has an equal and opposite component going the opposite direction. So what that means is that if there's a 50% possible chance to observe the electron in the 1s orbital orbiting clockwise, there's a 50% chance to watch it go counterclockwise. And so on average, it's not moving. Because half the time you see it move one direction, propagate the phase positively, and now the other half of the time you watch it move backwards, propagating the phase negatively. And so that total change is 0. Right, so the total magnitude is 0, but that doesn't mean that it's not moving. Right, so this means, this means that system or electron, let me say electron is moving, but is 50-50 clockwise and counterclockwise on average, which means that L squared, which means we get rid of the direction, is equal to 0. Okay, so this is a very small subtlety that Bohr did not appreciate. Right? Bohr got the right idea that, yeah, there should be some angular momentum in it. And the point is that there sort of is. All the states have angular momentum, and the electron is always delocalized around the proton, regardless of its state. But we don't actually measure angular momentum. We measure the square of the angular momentum, losing the directional information about angular momentum. And that is by definition 0, because there's an equal component in both directions, clockwise and counterclockwise. You've got a negative moving wave and a positive moving wave. You add those two together, they cancel each other out. Right, so the electron is moving, right? The 1s orbital is a sphere, which means the electron can be anywhere, right? So you can kind of think in some sense, right? If you observe the electron on the North Pole at one time and you take another picture, you'll find it somewhere else on the sphere at a different time. And so you can imagine that that electron in some sense is moving around the sphere from experiment point 1 to experiment point 2. And it has some momentum in the sense that it's moved. But on average, it looks every move that it makes, on average, there's an equal and opposite move that it makes as well. Okay, so the electron is perfectly delocalized. Does not mean it doesn't have angular momentum. It just means that when we measure the square of the angular momentum, it's 0. Okay, it can be going either way, no preference. Right, so Bohr is kind of half right, half wrong. And the reason why Bohr gets this wrong is he doesn't have, at the time, an appreciation for this idea that in quantum mechanics we measure squares. And you have to take the wave function square, the operator square. Didn't understand this, that hadn't been invented yet, that trick. This idea that quantum mechanics is about these squares and taking averages. He didn't understand that. And so he gets the right answer for, in some sense, for the wrong reasons. So when you go back and do Schrodinger's equation, you tackle real quantum mechanics, you realize he got the right idea, he's just not measuring the right thing. So applying this idea from classical mechanics, which is that we can always measure L, can't do that. You can only measure L squared. And therefore, the statistics of angular momentum look different to us because we're measuring L squared. We don't have any directional information. Okay. So that's kind of all I want to say about angular momentum for now. One more thing on actually, what is it? How do I know that Bohr's wrong? Experimentally, this is proven. Right? There's a really, really nice experiment you can do. So this is experimental validation. Against Bohr's model. Right, and it's an experiment called the Zeeman effect. All right, let me explain what the Zeeman effect is. So imagine I have a hydrogen atom. Right, so I've got this. I've got this vacuum chamber. Right, and inside the vacuum chamber, I have a hydrogen atom. Here's my H atom. All right, and I'm going to apply to it. Say I have some light here, and let me just go ahead and draw my spectrometer. So here's my laser. Okay, here's my laser. And then I've got a detector here. I'm going to shine a laser at it. But what I'm going to do is I'm going to apply a static magnetic field into my system. All right, so think like an NMR experiment where I have a magnet. So this whole thing is arranged by a magnet. And we'll just say that I have a magnetic field in this direction. So I apply a magnetic field B along the Z direction. All right, so we have a static magnetic field, BZ, that's lying along the Z-axis. I'll just draw my coordinate system here, Z, right, with strength. Right, and I tune my magnet to tune its strength, and we'll say that the strength is B0, absolute value. So some strength. And what I'm going to do is I'm going to measure the n=2 to n=1 transition, this Bohr transition of hydrogen between the ground state orbit and the first excited. Right, so I'm going to shine. First, I'm going to shine light such that the light, which is h bar omega, is around E2 minus E1, right? This is that Bohr transition, that first Bohr-like transition. Okay. And this has a special name. We'll talk about it next class. This is what's called the Lyman alpha line of hydrogen. And I'll give you the exact nanometers of it just so we have it for later. Yeah, so it's at 121.567 nanometers, which is in the this is in the ultraviolet. Right. This is one of the brightest transitions for hydrogen. Right. There's a lot of astronomy that's done with Lyman alpha. In fact, there's a really cool study people have done just recently published about 2 weeks ago. The world's largest historic study of hydrogen emitters in the galaxy and the universe. So they take a telescope and they measure the Lyman alpha line, and they use it as a calibration to atlas and map out all the galaxies, all of the hydrogen emitters in the galaxy that they can see in our visible sky. So it's all the external galaxies and all the visible stars. It's millions and millions and millions and millions of spectra, each corresponding to a different molecule, different system, different galaxy or a different star. And one of the cool things about spectra in space is that the farther the spectrum, the farther the source is away from you, the more, because the universe is expanding, everything is moving away from you. The universe is not only expanding, but it's accelerating. It's moving faster. Accelerates. It's moving. Things that are really, really far away look like, from your perspective, moving away from you very, very quickly. Right. So if I look at a galaxy that's 10 billion light years away, it's moving away from my eyes. It's literally accelerating, moving away from me. It's a moving object, expanding away from me. And because of the Doppler effect, it actually shifts the wavelength of the line, and red shifts it to higher wavelength. So sometimes if the further you measure the hydrogen source from a moving object, the more positive this wavelength becomes. It moves into the red, and you can calibrate that. You know how red shifted it became. Calculate its rough distance, because the universe is expanding roughly by the same amount. So if you know how far away it is, how fast it's moving, how much it's shifting, you can calculate roughly how far it is away from you. And people use this to, and a study that just came out is using this to actually measure the acceleration of the universe and its expansions. And everything is not only moving away from you, but it's getting faster in time. And depending on how you measure that acceleration, it's called Hubble's constant, you get different answers. There's what's called there's a tension in the value. Some different ways to measure give you different answers than other ones. And so people did this massive Lyman alpha study of everything. They measured that acceleration, the Hubble constant, and it's completely different than every other measurement before it. So we're not really quite sure why that is. But Lyman alpha is used spectroscopically in some sense as a standard candle, tells you something about distance. So it's very common to study this. So I digress. So what I want to do is I want to shine light at this, and then what I'm going to do is I'm going to turn my magnetic field on and off. I'm going to vary the field strength. Okay, and so I can make a plot now. What I'm going to do is I'm going to make a plot in my. I'm going to measure the spectrum of the Lyman alpha line as a function of the strength of the magnetic field. And this is what you see. So if I vary B naught here, and I measure the energy of the transition. So at zero field strength, I see this at 121.567 nanometers, which is, I'll calculate it really quickly in wave numbers for you. Which is 82,259 inverse centimeters. Right. And so you see, when you look at that line in your spectrometer with zero, you just see one line. And so we just see one line. So there's just one point here. And then what happens as you turn the field on, the line splits into three components. So one of the components, component one, does not change frequency at all. So component one moves like this, it just moves flat. And then there's a component that increases in energy linearly with the strength of the field. And there's a third line that increases opposite with the same slope, but negative. So there's three components there. Right? So at non-zero field, Lyman alpha has three components. All right, so why is that? Why does it have three components? All right, why is it Bohr predicts it to have one, right? Bohr says I go from the first orbit to the second orbit. There's only two orbits there. There should just be one absorption. But when you apply a magnetic field, that one absorption line becomes three. All right, why is it? Well, this is what's called the Zeeman effect. What the Zeeman effect says is that we can treat the Hamiltonian for the Zeeman spectrum. It's the original spectrum of the system. So this is the zero field, which is just n equals 1 and n equals 2 with a wavelength of 121.5 nanometers. And then what happens is it splits by this number that's proportional to the magnetic field, right? It's linearly proportional to the magnetic field. And there's an additional constant that it's multiplied by, which the problem set will talk about, G mu B. This is a constant. This is called the magnetic constant of hydrogen. Times M. And I'm missing a h bar squared here. Okay, so what this means is that with a field, with magnetic field, right, the spectrum splits by h bar squared v naught G mu B, which is just a bunch of numbers, times M. Okay, so let's think a little bit about the energy level structure of hydrogen and its angular momentum. So our angular minimum view, so in terms of L squared and M sub L, or L squared and L sub Z, right, we have, first we start with two states, n equals 1 and n equals 2. And we know that just from the original, from general chemistry, I'm just going to assume a little bit about general chemistry. Remember that the only orbital in n equals 1 is the 1s, right? So there's one orbital here, the 1s orbital. And then at n equals 2, right? The n equals 2 valence, there's 4 orbitals. There's the 2s, the 2px, the 2py, and the 2pz. Okay, let's just check. Okay. Yeah, we'll come back to this 1 and 2 next class, right? I'm just assuming a little bit about GenChem here. If this is not clear, we'll clarify it next class. And one of the things that we learned is that all in hydrogen, all the n equals 2 orbitals are the same energy. So that's what, as far as we know, they are. And that's what the spectrum shows. Again, what Bohr saw is one line. We saw n equals 1 to 2, which is something for the electron from this state going into one of these 4 states, all of the same energy. Give one line. And look, what the idea though is that when we turn the magnetic field on, these orbitals split based on their value of m. All right, so when we turn the field on, so then we set B0 not equal to 0. We turn the field on. Well, then these levels are going to change energy based on their value of m. Well, what are their values of m? Well, m for the s orbital, of course, is 0 because L is 0. And then we have the L equals 1 for the p orbitals. And they could be -1, 0, and +1. Remember, the 2pz is defined as L equals 0. Those are the x's and the y's. Right, and so what happens is when we turn the field on, the -1 state decreases in energy, right? Because the energy shifts as a function of m. M is -1 here. So this whole thing, the energy of it decreases linearly with the field. The +1 state does the opposite. It increases in energy with the field. It's a plus characteristic. And then the z orbital doesn't change at all. Nor does the s orbital, because m is 0 there. It doesn't couple to the field. So what we get instead are two states that are at the same energy, right? These are the S and the PZ. They're at the same energy. And then we split it, right? The +1 state increases in energy. And the m equals -1 state decreases in energy. Right? And the spacings between these is h bar squared v naught g mu b. You go do this experiment and it's completely reproducible. People have measured these splittings to extremely high precision. In fact, I think GUV is known to something like, I think actually it has infinite precision. But basically, it's one of the most precise things ever measured. You can measure it to 10, 12, 13 decimal points or something. And so what we actually see in the experiment, therefore, and let's do it for the lower state as well. I'm just going to adjust the energy just a bit, just to have some room here, right? Here, this is, of course, L equals 0, M equals 0, 1s, and so it doesn't change energy at all. Right? And then so the question, of course, is what do we see in the spectrum? Well, we see a line here. We see a line here. And then we see a line to the upper state, right? So now we see 3 lines instead of 1. We get 1 line without the magnetic field. And with the magnetic field, we get 3 lines. And this is what's called the Zeeman effect. Right? And it's the idea that the M states, right, the projections, so the magnetic field defines plus Z and minus z, right? One's preferred and one isn't. One preferred orientation. Causing states of different LZ to split. Right? The idea is that if the magnetic field is pointing in the positive direction, this, there is an M component, an angular momentum of that electron that in some sense moves with the field itself. The magnetic field has some oscillation like this, pointing in positive direction. There's one orientation of the electron that prefers to be aligned with the magnetic field, and there's one that is anti-aligned with the field, and they have different energies. In some sense, it's like taking a positive and a minus pole and putting another magnet next to it, and having the positives aligned and the negatives aligned is different than having them flipped. They have different energies. Right, so the Zeeman effect is the proof that Bohr was wrong, and in fact, the system of the hydrogen atom not only has angular momentum, but we can but it has not only total angular momentum, but also we can only measure one direction, LZ, because the system, the energy levels of the hydrogen atom split with LZ when we turn the magnetic field on. Right, they'll split anyway else. Right, so the only thing that this is consistent with is that structure that we've just enforced. L squared and LZ. Any questions about that? All right. I've already done, so you'll see I'm like, I think problem 2.1, it's just this again. All right, so just keep that in 2.1 is just to kind of go back to this problem again. To calculate things a little more precisely. And we'll look at this again when we come back on Thursday when we have all the hydrogen. Okay, so what I want to do now, I want to look at one other type of angular momentum. One other side. The electron has another type of angular momentum. In fact, every particle, regardless of what it is, has a value to this intrinsic angular momentum. We need to deal with it because it ends up being extremely important in chemistry. And this is spin. So let's think about spin a little bit now. This new type of angular momentum is what's called the spin angular momentum. Right. It's very, very hard for me, to use a top. Okay, with when I was doing regular angular momentum, again, we can think of rotating objects. And we can have this kind of classical analog to kind of think about rotation. You cannot do that with spin. There is no classical analog for spin. It's a purely quantum mechanical effect. And so I can't, it's very, very hard for me to sit here and compare it to something classical because there just isn't an analog. There just isn't something to correlate it to. The best way to think about spin is to think about it from the perspective of angular momentum orbitally. How are they similar to each other? So this is a pure quantum mechanical effect. And it's intrinsic, meaning you can't change it. It's intrinsic to the particle or intrinsic to an object. And unchanging. So I think it's just best to start thinking a little bit about the math of this, and then we'll apply it to the electron. Right, so spin as orbitals defined by two operators, right? And the operators work exactly the same as angular momentum. So the first one is s squared. That's the total angular momentum, or the total spin angular momentum. right? And then there's SZ, just like before, right? This is the projection on the Z-axis. Projection operator. Right, just like LZ. And this is like L squared. Right, they have the exact same properties, meaning that S squared applied to some wave function that satisfies it is H bar squared S plus 1 times psi, and SE psi is H bar, and we call this M sub S instead of just M times psi. Okay, and the rules are the same. M sub S is any value between minus S plus 1, S minus 1, and S. Okay, and S, it turns out, can be many different values. It's intrinsic to the particle. All right, so let me give you some examples. All right, so for instance, we just kind of jam them down here. So some examples of spin. If the electron has spin 1/2, right? It has what's called fractional spin. It's not an integer, but a half integer. Very interesting. The proton also is spin 1/2. What this is saying is that the electron has some angular momentum that you can't get rid of, some intrinsic angular momentum. It's always non-zero. And the angular momentum is 1/2 instead of 1. Right? So we're used to an orbital angular momentum having angular momentum 0, 1, 2, 3, 4. It can be any value, right? We can just keep spinning the electron up faster and faster. An integer amount. The spin angular momentum is one value and one value only. And it can be a fraction. Sometimes it can be an integer. It can only take one value. Right, so this value is always the same for the electron, regardless of when you do it. Here's another example. The atoms have a spin, total spin. So for instance, the spin of the carbon-13 atom. Oh, sorry, the spin of the carbon-12 atom, wrong atom. Which is again the most common atom, common form of carbon, has spin 0. It has no spin. The spin, oh sorry, it's not an atom. The spin of the helium atom is an integer 1. And then interestingly, the photon as well, another common particle we see, also has spin of 1. It also has intrinsic, the light has an intrinsic angular momentum to it. And so on and so forth. Now, you can always look them up. You can calculate them. All right, I just want to look at the math today. So everything has this extra intrinsic angular momentum that is, in some sense, completely separate from everything else. It's a separate angular momentum that the electron or the proton or any particle has that's fixed. It always exists unless it's a system that doesn't have any spin. And that's just due to coincidence. All right, so I want to look in particular at the 1/2 case, right? We're talking about the hydrogen atom. We have a proton and an electron, and they're both 1/2 spins. Maybe it's worth thinking about this situation. Let me give you just yeah. And if there are atoms that have much more complicated spins, so a chlorine, for instance, is spin 3 halves. Iodine is spin 7 halves. Bromine is spin 5 halves, and so on and so forth. Boron is spin 2. A bunch of other ones. So let's look at the example of the spin 1/2. All right, so let's just calculate a couple things really, really quickly. Really, really easy. Right, so let's imagine we have a wave function for an electron. This is our electron wave function with spin. And I put it inside of a box that measures s squared. Remember, I get h bar squared and then ss plus 1. That's the readout from my box. And s here, remember, is a fixed value. S is 1/2. Right? So that's h bar squared 1/2 times 1/2 plus 1, which is h bar squared times 3/4. I'll just clean that out. That's 3 h bar squared over 4. Okay, so this electron has some fixed angular momentum in it, the spin angular momentum, and it always has 3 h bar squared over 4 total angular momentum. Right? We can do stuff with that angular momentum, as we'll see in a second. The more interesting thing are the results of S sub c. How many stable orbits, if you will, spin orbits do you have? Right? S sub c tells us something about the multiplicity, right? How many possible orientations. So when we apply S sub c to omega e, we get h bar m sub s times omega e, or sorry, psi e, the wave function. And m sub s can be anything between minus s plus 1, s minus 1s, right? But s is 1/2. Right, so there's only two possibilities, right? M sub s can be plus 1/2, that's s. And then let's subtract 1 from that. 1/2 minus 1 is minus 1/2, which is minus s. So the only other option is minus 1/2. So there are what we call two spin states for the electron. Plus 1/2 and minus 1/2. Okay, right? We give these labels. Right, so some notation for you. We'll use this notation depending on the context. M sub s equals plus 1/2. We sometimes write the electron for this, or the wave function for this part of the spin. The label that chemists give it is what's called alpha. Right? So alpha is defined so that s squared of alpha gives you 3 h bar squared over 4 alpha, and s sub z alpha is equal to plus 1/2 h bar alpha. That's what we call alpha. There's what you guys have called it over the years. You usually give it a symbol. We often call it sometimes up arrow, spin up. So an electron is called spin up if it's in the plus 1/2 state. That's the convention. We often use a little arrow pointing up for that. And then m sub s equals minus 1/2. We have two labels that we often use for that. The spin part of the wave function we often call beta. That means spin down. Or we give it a down arrow, just spin down. Okay. So these are the two states. We call this the spin 1/2 doublet, right? Because it has two states. Spin 1/2 doublet. Okay. And this is the basis of NMR. Now we're looking at the electron here. NMR is about the nucleus, the proton. NMR is about the splittings of the ms states of the proton. The proton is also spin 1/2. And it also has alpha and beta, or spin up and spin down states. And the way that NMR works, let's think about what NMR is. This is, in some sense, the proof that spin exists. Experimental proof of spin is NMR. And it works exactly the same way as a bit like our Zeeman effect. This is NMR is a nuclear spin Zeeman effect experiment. Right, so you have a proton which has two states, plus 1/2 and minus 1/2. When the magnetic field is 0. And when you turn on the field, just like before, the spacing between them goes as G mu B B naught times M sub S, right? It splits by the M states, just like the Zeeman effect and an electron, and you get a state now of plus 1/2, sorry, minus 1/2 at low energy, and plus 1/2 energy. This is M sub S for the proton. Now they're at different energies, delta E. And if B0 is 1 Tesla, which is a standard magnet for an NMR, delta E is around 43 megahertz for the hydrogen, for the proton. Right? You can measure this very, very precisely. This is exactly how NMR works. When you look at an NMR, so for instance, the one that's up in CHEM, that's a roughly 50 megahertz NMR. What that means is that the field, the magnetic field, is just large enough, substantial enough to split the two M states by 50 megahertz. Okay, so that megahertz that you read on NMR specifies how strong the magnet is, and therefore how strong the Zeeman splitting between the two spin states are. So if you go to, say, Yale and you go use the 600 megahertz instrument, which is again like 2 meters tall, it's a really, really massive magnet. That magnet has something like 15 Tesla. So the idea is that the spin is a magnetically interacting angular momentum. It also is electrically as well, but we won't worry about that so much. It's mostly magnetically. Momentum applying a magnetic field causes causes spins to split in energy. That's the basis of NMR. I mean, there are many other techniques that use this as well, but NMR is probably the most common example. We use the Zeeman effect, the fact that spins interact with the magnetic field with respect to their projection number, plus or minus 1/2, and they do so in a linear way for the Zeeman. Sure, for almost 100 years now, it's been known, and of course we use it not only in chemistry, but we use it in medicine too, right? MRI is based on this concept as well. Yes.
So with masses on spinning, like positive magnetic and like spins.
Well, yeah, because there's the way I've written it here. M sub S is minus and the energy goes down. Because the energy shift is proportional to M sub S, since S is a negative number. So as the field gets bigger, the minus state gets more negative.
But spin doesn't change, right?
No, the spin doesn't change.
The more you actually, you're trying to.
What I'm saying is I'm making by decline of magnetic field. Okay, so let's talk about what these angular minimum kind of mean. So let's look at the vectors really quick. Can you give me 5 minutes to answer this question for you? This is a good question. So let's do our best to physically interpret what's going on here. All right, the idea is your electron has a fixed amount of spin angular momentum in it, right? And it's exactly the length of that spin vector is the square root of 3/4 h bar. Right, so you've got this vector, right? And there's two possible coefficients, two possible orientations, right? The first orientation is +1/2 along the z-axis, right? And there's an equivalent one pointing in this direction, which is the -1/2 state. Okay, so this is what we call beta, and this is what we call alpha. Okay, it's an angular momentum vector with either +1/2 or -1/2 component. Now, what if this were a classical object? What would that spin look like around the proton or around an axis? Well, so let's think about the electron as being a ball. All right, and the electron is propagating through space along the z direction, okay? And it has some angular momentum. All right, so let's think a little bit about the way that it's spinning. So it's moved, so the displacement vector of my electron in this axis is along the z-axis. Right, so my displacement is in this direction, and my angular momentum is in this direction. Right, so that means by the third order rule, that the axis of rotation is orbiting, it's oscillating around the z-axis in this direction outwards and counterclockwise. So what that means, if it's +1/2, so it's going counterclockwise, that's this way. It means that the electron has some helicity. Let me see if I can draw it just right. So if it's moving this way, so if it's moving towards me, it's going to be moving this way. Okay, so it's going to have, imagine it has a vector that's pointing out of it and it's oscillating in time. Like this. But remember, it's a wave, all right? So right, so this is +1/2. Right, so you can kind of think of it as, if you think about it as a wave propagating, the electron is a wave propagating towards you. It's got a fringe that's moving along the wave vector that's moving in a counterclockwise fashion. And so think about like a water wave moving on a line that's also rotating around that line. And it's rotating counterclockwise around the line of motion. Right, so this has CCW rotation. It kind of looks like a circular polarization. So this is kind of what a circular polarized electron does. Circular and polarized electron, which are the things that like polarized sunglasses cancel out, is an electron, or sorry, a photon, sorry, polarized light. It's a photon moving in some direction that its transverse component, remember, it's a wave of a complex, right? Of a complex component, a transverse component. A circular polarized photon is one where that complex wave is oscillating around the propagation. So you've got this wave that's like moving a helix around the propagation vector. And so spin, in the case of an electron in a magnetic field, a spin 1/2 electron is propagating with this counterclockwise helicity around the direction of propagation. And then minus 1/2 SC would be the opposite. The electron would be moving in the clockwise direction around the propagation of axis. It would look like a wave that's moving, that's oscillating in the complex direction. So let's see if I can do that. I'm going the wrong way. I think I'm going the wrong way here. Nope, that's right. That's right. This is clockwise direction. Okay, so the spin from and so another way to prove this is that you can couple this into linear momentum instead. So one thing that you can do, for instance, this is a really cool experiment. This is what's called the Stern-Gerlach experiment. Right, you could take a stream of electrons right? And so they're in, we'll say they're in a superposition of alpha plus beta. So you don't know if they're plus or minus, if they're up or down, they're just 50-50. And you put them into an S sub Z box, a box that measures the Z direction, which is a magnetic field. And so there's a magnetic field being applied here in this direction along the Z axis. And what you find is that the electrons that are plus 1/2 go up and the other ones go down in the Z direction. And so when you measure them on a detector, you don't find them in the middle, but you find a distribution, a bimodal distribution. Right, where the plus 1/2 and the minus 1/2 appear in completely different locations. They get split from the center being equal in opposite directions. Okay, so these are equivalent arguments. So you can either think of it as a complex wave, one moving in a clockwise fashion, one in a counterclockwise fashion, or if you project it into real space and you do a real measurement, find that when you apply a box, we measure the Z direction of the momentum with the magnetic field, and the ones that are plus 1/2 go this way, and the ones minus 1/2 go this way. They get deflected. Okay. Does this remind anybody of anything that we've done in this class before? Yeah, color and flavor. So, in fact, all right, so back to homework 1. S sub Z vector is the same as color. And X sub X or S sub Y, which are the ones that we can't know, are flavor. By definition, right? Electrons are black and white. They can be plus 1/2 or minus 1/2. That's what I mean by black and white. Right? So you've seen this math all semester. And now we're finally seeing it come back. This is what I mean by color and flavor. Color is one of the 3 directions. Remember, we can only know one of them. Just like L with S, we can only know one direction. I'm gonna make a joke about Harry Styles. I don't have a good one. So if we define things in terms of Z, we don't know anything in terms of X or Y, which is flavor. Right? And it works exactly the same way you would expect. If I separate my spins, the plus 1/2 or minus 1/2, imagine this is white, this is black. And then I take my plus 1/2 and I put them through a flavor box, an SX box. And then I measure S sub Z again, measure the color again. They split into plus 1/2 and minus 1. So let me just show you that. So this is the same as one of the experiments as before. Yeah, go ahead.
Not like.
The projection changes, but the total spin does not change. So I can change in the way that it rotates, right? I can move between -1/2 and +1/2, but the total angular minimum is always the same. It's still 1/2. Right? That number to S does not change. The projection can be different values. But the actual value, right? Every time I met, let me answer this question a different way for you in just a second. Right? If I put this into an SX box, it splits 1/2 and -1/2. And if I take this one and put it through an SC box, I only get -1/2 out. Right? So this is like color and color. And this is like color and then flavor. Same rules. So what was your question again? Okay. So the answer to your question actually, so you could write, so if you take an electron and put it through an S² box, right, you'll get two things out. One, you'll get the electron out. It doesn't matter what it is, it's always the same electron. And then your computer, this is my computer, an ancient computer, right? It always reads out 3h²/4. No matter what electron you put in there, right? So S is fixed. And I can put an S² box anywhere here. I can split them, I can put them back together, recombine them, do everything I want with the S and C. Every time I put S² in, I get the same outcomes around. Right, so S² has never changed, but the projection of S, how it's rotating might change. We can manipulate it. And this also is the basis of quantum computing as well. There are quantum computers that uses these spin manipulations, that manipulates the Z state of an electron or some sort of particle, and you can do calculations. If you have multiple electrons, you can build a computer out of these using spin states instead of bits. Okay, so I've got 5 minutes left. This is kind of all I have to say about spin for now. What we're going to look at next class is we're going to go back to the radial problem. We'll start thinking about the electrostatic interaction, all of this combined. And then what we're going to do is we're going to put everything together. We're going to take spin, orbital angular minimum, the electrostatic problem, the radial problem. We'll put them all together and think about what hydrogen looks like from a spectroscopic point of view when we consider all of these different effects, spin, orbital angular minimum, and the electrostatic interaction. Once we have all that together, we'll have a complete picture of hydrogen. We'll be able to start calculating things about it and understand exactly how hydrogen works. And that will lead us into other atoms from there on out. Okay. All right, have a good one, guys. Finished before class is over. Fantastic. That's rare for me. Oh, after that.
I'm actually really involved. And I also had to, I had to write out the butterfly. I know you're talking about. I always writing for that.